which have been executed on the database server. Because it's a dynamic view, sometimes the content of this table, of this view gets written to this particular table, $$_SQL text, and in that case, these queries are actually permanently logged within the database. Similarly, in MS SQL, you can obtain these queries forensically by calling the plan cache. So this is how the query will look like when it will be run on the server. As you can see, the clear text pan and the clear text string would be present in the SQL query when it runs on the server. So if you query SQL_text column from $SQL, then you will find the clear text pan and the clear text string more importantly. So these are some screenshots which says these are the strings. Similarly, you can obtain plan cache in MS SQL. So if in MS SQL, here is an example of somebody MD5 hashing a credit card information within the database. So if you look at the bottom half of the screen, the data in the database is MD5 hashed and it's safe. But if you obtain the plan cache, then you will find that the plan cache contains the clear text pan number. So that to me is a fail. Right. So when we talk about SQL injections, we talk about some really complicated hacks, and sometimes we miss out on some easier versions. So we were investigating a SQL injection, a breach from SQL injection, and when I found this particular attack technique, which I thought was quite neat. So let me actually, I've only got 5 minutes, so it's best to run the demo before this man throws me out of here. Okay, so stealing unencrypted card data from the database when it's not stored as clear text. So we have our e-commerce shopping application. Any resemblance to any application is purely coincidental. Right, so you choose a page, you click on buy now. It follows PCI compliance, so it goes over a secure page. You log in, supply your credentials, select the item, enter your card number, details, and basically just buy the product. Right. So what happens if in such an application you find a SQL injection? As we saw earlier, that this particular application has a different application server and a different database server. So even if you compromise the database server, you will not have the key because the key is stored in the application server. You can use the attack vector, which I mentioned earlier, but to query $SQL table, you must have DBA privileges. So what if you don't, like in this example, then you cannot obtain the queries forensically, so you are pretty much stuck. So we find a blind SQL injection in this application. So we do some and 1 = 1 and 1 = 2. Right. And then we run some tools to exploit SQL injection. So we run bsql-bf to exploit this particular vulnerability, and we do some basic exploitation. So we find we are running queries with Scott user, which is a really limited user, so we can't really query $SQL to obtain the queries forensically. We find out what the version is. Maybe can we do privilege escalation, and it's actually an Oracle 11G 1.0.6. So I mean, we don't really know of any privilege escalation vectors against this database, so it looks fairly secure. Now we find a card number table from credit card table, and if we extract the data, then we find the data is actually encrypted. So unless we have the private key, the decryption key, this data is virtually useless to me. So this is how the Whitebox side things look like. The application server connects to the database server, which is a different IP. It's using the Oracle's triple-des encryption for encrypting strings. The string is stored in the application server. I can possibly compromise the database server, but that will mean that I still don't have the private key, the decryption key. Right. Next, what the attacker does is he logs on to the server and he observes something. What he observes is that when he logs in on that payment page, he sees his full name displayed on the screen. So this particular data, his first name or his first name, last name, is actually a session data coming from the database, and that will be true for every single user who logs on to the application. So what if he can poison this data for every single user to contain a JavaScript keylogger? So he does that. He runs some massive update statements to alter the database and contain a malicious JavaScript on that web front end. So he issues a series of 3 commands, one after another. Okay, the looks are changing, so I'll just rush. Okay, so once he does that, and then now the victim logs in, then you will see that the data coming from the database, the session data, has now changed, and it now contains a JavaScript which points to the beef server. So what we are doing over here is we are not hacking the data within the database. We are hacking the data which is about to be written to the database before it touches the database. So when an end user logs in, this JavaScript will connect back to the beef server. So if you configure your beef server, then you will find the zombies connecting back to the beef server. So here we go, the zombies are connected. And then if you go back to the victim screen, then what you will find is, okay. Yeah, and then if he enters his details again onto that page, then you will find all that is available via our JavaScript keylogger, and it is sent out to our beef server. So who really cares about the data in the database if you can obtain it like that? Okay, so I've been asked to leave the stage. That pretty much is the end of the presentation.